I'm about to plug in this fan to test whether blowing on this sail will move the boat forward. And then I'm flying 4,000 miles to the equator, where I'm actually standing in both the northern and southern hemispheres, because this line here is the equator. And I'm here to investigate whether or not this demo for tourists is actually a scam. Basically, they pour water in this basin, and on the north side of the equator, it seems to swirl and drain counterclockwise, but just a few feet away in the southern hemisphere, the water seems to drain in the exact opposite direction. It's sort of like how you also might have heard toilets flush in opposite directions on different sides of the equator, and we're here to uncover the truth. But I'm not stopping there, because today we're gonna investigate 6 other physics and engineering puzzles using simple demonstrations as we go, because our goal by the end of this video is for you not just to know the right answers, but more importantly, for you to understand why they're the right answers. To kick things off, speaking of hemispheres, did you know the moon in the sky looks like this in the northern hemisphere, like in Canada, but it looks like this in the southern hemisphere, like in Australia? It's upside down! And while that is a fun fact, it's even more fun to understand why. And this is why. As we all know, the Earth is a sphere. So if you were Superman standing at the North Pole in the northern hemisphere, you'd look like this. But if you were Thor standing in the southern hemisphere in Antarctica, you'd look like this. Now, of course, the moon over here orbits around the Earth like this, and I'm gonna add an arrow to it to help us with orientation. And so to Superman at the North Pole, that arrow would point up, but from the perspective of Thor at the South Pole, that arrow would point down from his perspective. And now I know what you're thinking. If all that's true, then which way would the arrow point if you're Spider-Man standing here at the equator? Well, according to our model here, it should be sideways. And sure enough, here in Ecuador at the equator, I'm happy to report that the moon does in fact appear to be sideways. For fun fact 2 of 7, if you just stick 2 pins into some cardboard like this, and then connect them with a string and trace it out, you get my favorite geometric shape, an ellipse. But there's something really special about these 2 pinholes. They're called the focus points, and any straight line you shoot out in any direction from one of the points will bounce off the wall of the ellipse and always hit the other focus point. And here's proof, because I've got a laser pointer at one focus point, a ball of wax at the other, and a mirrored surface all along the interior wall. And now you can see no matter which way I point the laser, it always bounces off and lights up the wax. But here's the really cool part. If you build an actual full-size room in the shape of an ellipse, and then you stand at one focus point, you can hear even the faintest whisper from anyone standing at the other focus point, even hundreds of feet away, because all the sound waves bounce right back to your ears. In fact, this actual ellipse-shaped room was built by John Quincy Adams in the US Capitol building. And legend has it, he was a master at anticipating the moves of his opponents plotting against him on the opposite side of the large hall. And now that you know the physics involved, it should come as no surprise that John Quincy Adams conveniently placed his desk right on top of this leftmost focus point. Next up at number 3, everyone knows when you slam on the accelerator pedal in a car, the stuff inside slides backwards, and then when you slam on the brakes, the stuff inside just keeps moving forward. Including you, by the way, which is why we wear seatbelts. So then why the heck, when I'm driving to the birthday party and I have to slam on the brakes, does the cake slide forward, but the balloons actually move backwards? As for the cake sliding forward, well, that's just Newton's first law in action, which basically says all stuff is kind of lazy and wants to stay still unless a force comes in and tries to move things. And then Newton's second law tells us that the more you weigh and the more mass you have, the more force is required to even get you to move. But here's the thing we sometimes forget. The air around us is a fluid, and it also has mass. It weighs something. This is why air pressure is a thing. There's tons of air molecules stacked up above us, and they each weigh just a tiny bit. So we are like at the bottom of this air molecule dog pile. This is why your chip bag expands when you head up to the mountains. It's because it's moved up the dog pile. Now there's less air above it, weighing down, pushing in on all sides. And for a little proof, here's a simple demonstration that the air molecules around us do actually weigh something. When I throw this balloon at the side, it moves, but it doesn't quite knock it over. Now all I'm gonna do is take that exact same balloon and just add air. That's it. Everything else is identical and unchanged. And yet now, it bonks the sign over. So that means we increase the mass only by adding some extra air. Because again, Newton's second law states, the heavier, the more massive a thing is, the better it is at bonking things over. So in the car, when you slam on the brakes, it's not just the stuff in the back that has mass that wants to keep moving, but all that invisible air does too. So when I slam on the brakes, the air itself also sloshes forward. And since that air is more dense than the helium gas in the balloon, the lightweight balloon gets forced backwards. And that's what we'd expect, right? We say a helium balloon floats in air, or this ping pong ball floats in water, but it's almost more like the heavier, more dense thing, in this case the water, rudely cuts to the front of the line, forcing the poor ping pong ball up and out of the way. In fact, you can see if we lay this jar on its side, the same thing happens as in the car. When I give the jar a push, the water sloshes back, which forces the less dense ping pong ball forward, and then when it stops, the dense heavy water sloshes forward, forcing the ping pong ball back. Then for number 4, we're back here on the lake to figure out if sailboats move by having wind blow in their sails, why don't they just get a big old fan like this to power them through the water? Sort of like the guy in this viral video who's using a leaf blower, pointing into an umbrella to scoot his way around on a skateboard. Well, let's think this through with a simple demo of a fan that's attached to this train car. When I turn the fan on and it blows air to the right, which way will the car go? Well, of course it goes to the left, because it's basically cutting through the air and pushing it backwards, which creates an equal and opposite reaction that pushes the train forward, just like an airplane propeller pushing air backwards moves the plane forward. It's no different than me standing on the skateboard, and when I push watermelons to the left, they push back on me, so I roll to the right. Nate! Again? And so now let's place a brick here so this car can't move, and then add a second cart here with a sail. Now when I turn the fan on, which way will this cart move? Of course to the right, because all that fast-moving air hits the sail. It's like it's being bonked by all those tiny little watermelons. So if we now remove the brick, and this cart wants to move to the left, and then this one wants to move to the right, what'll happen when we connect them? Nothing, because it's a perfectly timed tug-of-war, with each cart trying to move in opposite directions with the same amount of force. A fan actually sort of does work to move a boat forward. You just have to lose the sail and point it the other way. But at that point, you might as well just take that same fan and stick it underneath the boat, so you could much more effectively push against the heavy water instead of just air, which is of course exactly what a boat propeller does. And sure enough, when I plug it in real life, as you can see, I don't go anywhere. So then if we've totally debunked the idea of blowing your own sail, then what about that guy with the leaf blower and umbrella on the skateboard? Well, I've copied his exact same setup here, and I can confirm it actually does work. Yeah! It just has nothing to do with the umbrella or the leaf blower, and everything to do with the fact that this is an electric skateboard with the battery stored right under here, exactly the same as you can see in a bunch of these shots from his video. Now, before we get to the last 3, including answering if this demo for tourists is a scam, if you're like me and you love that aha moment when you learn something new, well, I got great news for you.
Let me guess, Crunch Labs?
I'm glad you said it, Jimmy. That's right, because packaging up that moment is why I created Crunch Labs, where you get a super fun toy every month in the mail that comes with a video where I teach you all the juicy physics that make the toy work.
Mark won't say this himself, but obviously he used to work at NASA and Apple. He's one of the greatest engineers you can ever find. And he's specifically designing these boxes to teach you all the stuff he learned. He had this water gun that we made, and you can flip a switch when you give it to someone else, and it shoots back at you. I mean, it's awesome.
I've pranked you a couple times with the boxes, Jimmy.
I know.
So if you want to prank Mr. Beast while experiencing a bunch of those lovely aha moments at the same time,
it works.
Just visit crunchLabs.com to learn more.
Yes.
Now coming in at number 5 is the craziest fact I know. Imagine I just finished tying this rope all the way around the world. But now I just found out it was supposed to be a foot off the ground the whole way around. So the question is, how much more extra rope would I need to buy to add to this rope to make that happen? Now you might be thinking double or even triple this amount, but what if I told you you only need this much extra rope? 6.28 feet to be exact. Think about that. The circumference of the Earth is 131 million feet, and yet you only need this much extra rope to lift the whole thing a foot off the ground all the way around. And what's even crazier is if you did this around a basketball, it would be the exact same amount of extra rope. Now the math is just some straightforward 8th grade algebra, and you can see here, because the radius cancels out, it doesn't matter what size circle you use. It always works out to 2 pi, or about 6.28 feet of extra rope. But But if math isn't your thing, don't worry, because if you just pretend the Earth is a square, it will immediately be obvious why the size of the object doesn't matter. So if this is my initial rope, when I raise it off the Earth by 1 foot, you can see in each corner, I only need 2 extra feet, so 8 feet total. And just like with a basketball, you'd still get the same answer if you tried it on a smaller 4-sided shape like your TV, which is pretty close to the 6.28 extra feet needed for a circle. And number 6, there was a Kickstarter a while back that claimed to have invented a floating backpack that reduced impact forces by 86%.
Welcome to the future of backpacking. You've never seen a backpack that moves like this, or that lets you move like this. And this motion isn't just for show. By suspending the load, Hoverglide reduces impact forces by 80 to 90%.
I really took an interest once I noticed a lot of people in the comment section were debating whether or not this would actually help. So what do you think? Is this a scam? The case for it not being a scam is that when you wear a normal backpack, as you bounce up and down, with each step you take, you're working against gravity as you move that entire weight up and down with you as well. Sort of like pulling this weight up and down with a stiff rope. But if the backpack was elastically suspended on a track, its own inertia would tend to keep it vertically in the same spot. So you could still bounce up and down while the pack wouldn't move. It would be like replacing that stiff rope with an elastic one, at which point you can see it makes it a lot easier on my arms moving up and down as the weight stays in place. But the naysayers pointed out all the pulleys, cords, and extra frames to make the system work is still an extra 4 pounds of weight, and whether it's bouncing or not, you're still carrying 4 extra pounds to the top of the mountain. Plus, the video just shows the ideal use cases, and in real life, it probably wouldn't work that smoothly hiking over rough terrain. And I felt like both sides sort of had valid arguments. So as a firm believer in the scientific method, I ordered one myself and then went hiking for a few miles with the normal backpack, and then put the exact same amount of weight in the Hoverglide backpack to qualitatively compare the difference.
So far, I don't like it. Feels like it's like rocking me back. Let me try jogging. Oh, that feels good. That's kind of the trick, I feel like. If you hit the right cadence, it's magical. If it's not the right cadence, it's the opposite of magical. Oh yeah, now it's... And then it gets out of sync, throws you literally off balance.
So my verdict is that on flat, predictable terrain, it can be beneficial. But on any sort of rough, sporadic hiking terrain, it's just not worth the extra weight and force from out of sync issues.
And for our final science challenge, we're back here at the equator in Ecuador to see if this popular demonstration for tourists is actually a scam.
Does the water really drain in opposite directions, even just a few feet on either side of the equator? And relatedly, do toilets also swirl in opposite directions in the northern versus southern hemisphere? Now for the toilets, let me just debunk that myth out of the gate. Because if you look closely, the swirl direction is just a function of which way the nozzles point, as you can see here, and with any toilet you inspect yourself. But what about sinks that have just a drain, like in the demo here, where there are no nozzles? Well, believe it or not, there's actually some truth to this idea because of something called the Coriolis effect. And it's the same reason you might have noticed weather patterns like this spinning counterclockwise in the northern hemisphere, in which case we call them hurricanes, and clockwise in the southern hemisphere, in which case we call them cyclones. And the reason for this is pretty straightforward to understand if you imagine you have a very big sink that spans from the equator all the way up to the North Pole. In that case, a single drop of water in the sink at the equator here is going for a joyride really fast as the Earth spins, and a drop of water near the middle is moving at a medium speed. But a drop of water at the North Pole isn't moving at all because it's right on the axis. So now when you pull the plug on the sink and the water moves towards the middle, the drop here is suddenly moving laterally much faster than the slower water that was near the drain, so it gets out in front of the drain. And conversely, a drop here at the North Pole is laterally moving much slower than the water near the drain, so it falls behind. So when all the drops are affected this way, you naturally get a counterclockwise swirl, just like a hurricane, where the eye of the hurricane is the low pressure zone like a drain. And then of course, applying all this same logic to the southern hemisphere would naturally do the opposite, resulting in a clockwise swirl. So does this mean that sinks do in fact drain opposite in the northern and southern hemispheres? Well, sadly, no. Because the Coriolis effect is really only noticeable the greater distance you're moving up or down from the equator. So unless you have a 5-mile wide sink, or if you make the most perfect of perfect conditions like my friends Destin and Derek showed,
the water is flowing clockwise due to the Earth's rotation.
The water's going counterclockwise because I'm in the northern hemisphere. It's real.
This effect is way too small to have any meaningful impact on the swirl directions of sinks and toilets, at which point it comes down to other factors like sink geometry, or the fact that the seemingly still water was actually still barely moving around when the plug was pulled. So then what about that tourist demo? Well, if you play it back and look closely, you can see at the end of his pour, he does this subtle twisting motion. So the water would just continue to swirl in the direction of the twist. So when he finishes the pour here, he twists this way and the water continues swirling that way. And then after moving the sink allegedly over the equator, he finishes his pour twisting the opposite direction. And then the water swirls in that opposite direction. In fact, you can easily recreate this demo yourself at home to see that by copying this method, you can also easily get a whirlpool in both directions. And therefore it should come as no surprise that when I ask this question,
Does it work even like if I pour the water?
I was denied the opportunity to test and observe. On top of all that, as the final nail in the coffin, if you actually look up the GPS coordinates of this place, it's more than a football field away from the official equator, which means we were actually in the southern hemisphere the whole time. So instead of actual science, this is just an attempt to take your money with nothing more than a lame magic trick, where the real magic is all that new juicy knowledge I just wirelessly transferred through that screen you're watching me on from my brain into yours. It's a new year, which means it's a great time to invest in that passion for learning. Because that passion is not only the main driver for why I make these YouTube videos, but it's also why I created Crunch Labs, where we ship a really fun toy to your porch every month. And not only do you learn how to build and think like an engineer, but you learn the fascinating physics and engineering principles that make the toys work. Every month is a new principle, and the best part is, just like how you hopefully enjoyed watching this video, it doesn't feel like learning, because we're real good at hiding the vegetables. And what I mean by that is 87% of kids rated an 8 through 10 on a fun scale out of 10. But also more than 3 out of 4 parents said their child gained a new passion around STEM and engineering after getting the build box. Yes. On top of that, each month your box has a chance to contain the platinum ticket, and if you get it, well then you're coming out to Crunch Labs to build with me and my team for a day. So if you want to invest in the superpower of having a passion for learning, just go to crunchlabs.com or use the link in the video description to get your Build Box subscription today. Thanks for watching.